Hi, my name is Jason Grant. I'll be presenting our poster on the Enzyme Lab. So my group, we wanted to test the optimal temperature for trypsin's functionality. A little bit of background, an enzyme, it's a biological catalyst. The way it works is enzymes, they actually speed up chemical reactions, but they remain unchanged and they lower the activation energy of chemical reactions. So by definition, they're catalysts. They're made up of proteins. Proteins are molecules that are consisting of long chains of amino acids. They're essential for a variety of functions within organisms. So enzymes, they just assist in the breakdown of these proteins into their amino acid forms so they can be reused and built up into other proteins. The enzyme trypsin itself, it's a protease enzyme. It's found in the small intestine in mammals, but it's also produced by some bacteria, secreted by bacteria. The pancreas in mammals, it's what produces trypsin. It actually produces trypsinogen, which is then react with enzymes in the small intestine to create its active form of trypsin. Trypsin itself, it catalyzes the breakdown of dietary proteins. The one we'll be using is azocasein. It's a milk protein. It uses a protein hydrolysis reaction, so it cleaves the bonds between the arginine and the tyrosine amino acid groups. So it pretty much breaks it down into smaller chains that can be reused or further digested and then reused. So our main question is the functionality of trypsin affected by temperature. We believe that at temperatures lower than human body is at 37 degrees Celsius. We tested 17, 27, 37, 47, and 57. So we thought that at 17, 27, it would be lower. And then at 37, it should get higher. 47 will probably be around optimal. And then after 47, it should start to drop off, which is why we tested 57. The reason we think this is going to happen is if you increase heat, you're raising the energy within the system, so the molecules will be moving around faster. You increase the rate of motion. That'll cause more collisions between your substrate and what you want to react with it, which will cause a faster rate of reaction. But this will only go on for so long because eventually the proteins that make up the enzyme will start to denature. When they denature, these proteins are made up heavily very complex structure, consists of 4 parts. So their function is based on their structure. If their structure starts to come apart, which is what happens when too much heat is put into it, then it loses too much, or it loses its functionality. So for our parameters, as stated before, 17, 27, 37, 47, and 57 were the temperatures tested. We wanted to test parameters that were close to the small intestine of the human body, which has a pH of 8 and a salinity content of 0.15 molar NaCl, or close to it. So we use our buffer with a similar salinity content and pH. Our materials, we had our reaction buffer, our substrate, which is the azocasein, our trypsin, which was the enzyme we wanted to test, our trichloroacetic acid, temperature-controlled water baths, micropipettes, spectrophotometer with cuvettes, and our centrifuge and test tubes. So the first thing we did is we created our experimental groups for each temperature. It consisted of 450 milliliters of our buffer, 500 milliliters of our substrate azocasein, and 50 milliliters of trypsin. We had 3 replicates for each temperature, so we had 5 temperatures total. We had 15 experimental groups total. Next thing we did was we made our control groups. We had a negative control for every experimental group that we tested. They were created the same way as the experimental group, but instead of the 50 milliliters of trypsin, we added 50 milliliters of a reaction buffer, because the point of the negative control groups is to show any breakdown of azocasein that was not catalyzed by the enzyme. And the negative control groups, they also, the reason they're set up identically to the experimental groups, but without the azocasein, is we want to rule out any other variable that could possibly affect the breakdown of our substrate that wasn't catalyzed by the enzyme. So once all of our tubes were constructed, they're incubated at their assigned temperatures for 20 minutes. After incubation, we added 500 milliliters of our 10% TCA solution. It stops any reaction that's going on after the incubation period, because we don't want any data that has to do with not the incubation period. It also causes any macromolecules like the undigested azocasein or any leftover trypsin to fall out of solution. So once it falls out of solution, we can centrifuge the test tube. We did it at maximum for 2 minutes, and it'll cause anything that's fallen out of solution to pellet at the bottom, which would be the undigested azocasein or the leftover trypsin. So the only thing that won't be pelleted will be the liquid at the top, and that will contain the broken down azocasein. So we transferred that broken down azocasein supernatant out of the centrifuge tube into a cuvette, and we use that for spectrophotometry. So before we could actually read our absorbance values, we had to blank the spectrophotometer, and the way we did that is we put distilled water in a cuvette and read the absorbance at 440 nanometers. So doing that, distilled water shouldn't have any absorbance at 440 nanometers, so that's kind of a way to calibrate the instrument. Then we observed and recorded the absorbance of each of the experimental cuvettes and the spectrophotometer at 440 nanometers. The reason we did it at 440 nanometers is because prior to anything, we added sulfanilamide to the azocasein, which is kind of like a tag for it because it allows you to, it will absorb light at 440 nanometers when it has been broken down by trypsin. So it allowed us to measure the amount of azocasein that was actually broken down in the reaction. So here's the results. You can see the individual results for each trial, followed by the averages. All of the control averages were very close together. They had very low absorbance as expected because there shouldn't be any absorbance because none of the azocasein should have broken down. So our averages for the experimental groups, you can see over here, it's a steady curve rise, almost exponential in nature. They seem to go up by about 10% on each of these, and then they start to double towards the end. There was low variability between the groups in general. I mean, you can see some higher variability here in these standard deviation bars that have been added on, but it was very low at the beginning, but that was overridden by the pretty big difference in averages among the experimental groups. So since there was a big difference in averages and low variability, that resulted in a pretty low p-value when we did our t-test. All of our t-test p-values were below 0.05 for every group that we tested. And we could test every group because we had a control for every group that was an experimental group. So our results, they were significant, or statistically significant, and we can confidently conclude that reaction rate will increase as temperature increases, at least for the temperatures that we have tested. So our experiment, it effectively measured the effect that temperature has on enzyme rate, but we did not find a denaturation point. There is a small chance that our maximum was actually between 47 and 57, so somewhere up here, and we're starting to catch the down slope after the maximum, but that's a small chance, and the only way we can test for that is adding more increments, and we could also add some temperatures above 57 just to make sure we're not still on the upswing. So no other groups tested for temperature as far as the rate of reaction goes. They all tested for pH. So if we really wanted to find where trypsin's maximally effective, we could combine their results with our results and test around the pH of 9 because they found pH 9 to be optimal. But we're not looking for optimal pH. We're just trying to see if the optimum conditions for trypsin would be human body conditions, which is not what we found. So we spoke about some possible improvements briefly. We could add some temperatures above 57. We could add some smaller increments between 47 and 57, so on. Our control parameters appear to have resulted in our exceptionally low absorption values, which means they were properly prepared. So the reason all this is relevant to bacteria growth in general, we determined that the ideal temperature to react azocasein with trypsin is somewhere above 45 degrees Celsius, as you can see here. Max could be around here, but it's most likely further up. So in order to further narrow this, we'd have to test some higher temperatures and smaller increments. So what this shows is that trypsin, it is reactive within the small intestine, but it's not at its optimum point. So the small intestine most likely requires a rate of reaction that is lower than the optimum for trypsin. So that's about it. You can see here some of the citations I used for the information, and thank you for your time.